This presentation is Catching Insider Data Theft with Stochastic Forensics. Jonathan Greer is an independent security consultant who works with clients around the country with forensics and security issues. He is presenting today about a new method that he has developed to detect insider data theft. Let's give him a hand.
Good morning, everybody. My name is Jonathan Greer. And like Heather said, I'm going to be presenting a method which I developed to catch insider data theft. This is a method which I developed in the course of an investigation that a client of mine requested. Like Heather said, I'm an independent consultant. And I had a client who was very, very concerned. He had reason to believe that a high-level employee had perhaps stolen some very valuable data. And my client was very, very much in great need to find out if this was true or not. And the problem with insider data theft is that it's a lot harder to investigate than a typical external penetration. Right? If you've ever investigated on external penetration, there's lots of broken windows. When people break in, they leave traces of how they broke in. And we can use that to investigate. But an insider case of insider data theft is much harder. Because the insider has access to the data, they have technical authority to use it, they're using it every day. And it's very difficult to distinguish between authorized usage and unauthorized usage. Anyway, this was the predicament my client was in. So when I started on this case, I did some basic research. And here I have a quote from forensics expert Harlan Carvey. This is from his great book, Windows Forensics Analysis. And Carvey deals with this problem. And I'll read you what he writes. He writes, I received a number of questions asking about data exfiltration. There are no apparent artifacts of this process. Artifacts of a copy operation are not recorded in the registry or within the file system as far as I and others have been able to determine. So Carvey basically said we're stuck. He says there are no artifacts from this process. When you copy a file, there's no way to tell if someone copied it versus if they were doing anything else with it. And since there are no artifacts, there are no forensics. Carvey says we're stuck. And my client was in a big mess. So I set out to challenge this assumption, to find out, is it possible to do forensics without any artifacts? Now, it sounds kind of funny. Normally, the way we do forensics is we look for artifacts and we piece those artifacts back together to figure out what the person did. But maybe there are some novel approaches, some new ways to doing forensics. So let's take a big step back and forget about forensics for a moment. Let's look at a file system. Now imagine, this is just a typical folder on any computer. Imagine that I sat down and I was using this folder. I was using it for 20 minutes. And when I got up, I asked you, please take a look at the file system, examine it, and figure out, what was I doing? Was I using it in the course of doing my business, or was I copying this entire folder? So what might you do to figure that out? Well, we know there's something called an access timestamp. Whenever I open a file or a folder, the OS will record the time it was last opened. For instance, if today at January 26th at 3 p.m. I open up a file, let's say the McCarthy-Smith document, the operating system will write down it was last opened at 3 p.m. January 26th. Now that's a very short-lived data. If tomorrow you open it up, it will throw out the 3 p.m. from today and write down January 27th at 11 a.m. Just records the time of last access. Okay. But what would happen if I was just using this routinely? Well, I might open up the Project Aurora folder, open up the engineering folder, open up the test folder, open up the heat spreadsheet, and then open up the vibration spreadsheet, look at it for a few minutes. I might get a coffee and come back, immediately open up the McCarthy-Smith document, go back to the blueprint document, jumping around the folder as I'm doing my business. If you would look at the system when I got up, and you would look at the access timestamps on the system, you'd see pretty much a random pattern. Open this up, jumped over here, got a coffee, jumped over there. Okay, great. Nothing here is very significant, nothing here is very interesting. The fact that this was opened at 9:13 versus 9:14 doesn't really tell us anything we need to know. Okay, great. Now let's imagine that instead of using it to do my business, I copied it somehow. I put it in a USB drive, I loaded it off the network, however I copied it. So what would happen now when I decided to copy the Aurora folder? Well, Windows would open up the Aurora folder, it would enumerate its contents, it would see that there's the engineering folder inside, it would open that up, see that that folder has some subfolders, It would descend down, open up the first subfolder, look what's inside it, the blueprint file, open up that file, copy that file up, and keep on going in a very well-ordered pattern. Instead of jumping around randomly, Windows would recurse down the directory through each file and each folder, copying them one by one. Now when I got up, and I handed you over the file system and said, please take a look at it, you'd see a very different pattern. Now, it's true, none of these timestamps are interesting in their own right. And there are no artifacts. But if we look at the relationships among the timestamps, that is, we look at the patterns and the properties which emerge, we see a very different type of pattern. We see a very well-ordered pattern, opening up the first folder, go to the next one, go to the next one, continuously descending down in a very well-ordered pattern. None of these timestamps tell us anything, but the relationships among them cause certain properties and patterns to emerge which are quite significant. So again, while I was working on this, I was able to think of 4 different types of emergent properties which we can use to distinguish routine access from copying. Routine access is selective. Right? I open some folders and some files, I don't open all of them. But when you copy, it's non-selective. It's very rare in cases of data theft that the person will take the time to cherry pick individual files. They'll usually just copy the entire folder, hook, line, and sinker, and take whatever they have. Number 2, routine access is temporally irregular. I might open up one, open up another, get a break, take a break, get a coffee, come back. There's no continuous usage of time, whereas copying is continuous in time. The OS copies one folder, the next folder, going through without taking a break. And number 3, routine usage is randomly ordered. I open up one file, jump around, open up another one. There's no way to look at the file system and predict what I'm going to open and what I'm not going to open. Whereas copying is recursively ordered. It's a very clear, well-defined order, which is the same every time you copy. And number 4, when you do routine access, you'll very often jump to a file without going through its chain of parent folders. Right? I might have that file on the list of recently used files. It might be in my recently opened documents in Word. I might know the file name. For whatever reason, I can just open it right away. Whereas when I copy a file, when I copy a folder, no child is going to be opened before we get to the parent. So with these 4 characteristics, these 4 emergent properties, we can in fact distinguish routine access from copying. So without any artifacts, we can do forensics. Now this idea, it's a very novel idea, but it's very simple. It prompted a colleague of mine to say, slap your head and say, duh, wish I thought of that. Okay. So these are ideas going through my mind when I'm trying to solve the case. Of course, this is useless so far in the real world. Right? I gave you the luxury of looking at the computer 20 minutes after I used it. But in real life, you don't have that luxury. In real life, when you're in an investigation of data theft, you're coming in days later, weeks later, sometimes months later. We heard yesterday the keynote Sean Henry from the FBI said about cases where they're coming in years later. And timestamps, like we said, don't last. The second I get up and someone else sits down to use that folder, they're going to be overwriting all those access timestamps. The second they open something up, they're overriding the time that I opened it up. That's the first problem with what we have so far. And the second problem is that, okay, great, so these properties distinguish copying from routine access, but there might be other types of access besides routine access and besides data theft which have similar properties, right? If you've ever used the grep command and done a recursive grep searching through folders and folders, maybe that causes similar patterns. Okay, so we're gonna explore both of these problems. Let's start with the first. So like I said, seemingly this method is worthless unless we're investigating right afterwards. Because the second I get up and someone else uses it, all that timestamp information is overridden. Okay. Here's where the idea of stochastic forensics come into place. A stochastic process, by definition, is something which is unpredictable, but it's unpredictable in a precise way. The classic example of this is physics when we want to look at a gas. Imagine we're trying to study a gas, and the gas has zillions and zillions of particles. Each one of them is vibrating and bouncing around and jiggling in very complex ways. And if we wanted to use Newtonian physics to analyze the gas, we're stuck. We just don't have enough information to do it. Even though we believe that all the particles of the gas follow laws of physics that Newton discovered, we just don't have enough information. It's too unpredictable for us to apply them. So along came Boltzmann and other physicists, and they invented something called stochastic mechanics, which basically says, It's true, we don't know the properties of every particle. And we don't need to know them, but we can make statistical models of how particles behave. And precisely because there are zillions of particles, the law of large numbers holds true. We don't need to predict every individual particle. We can talk about trends. And we can use those statistical trends when we use the language of math to make big predictions about how the gas will behave as a whole. So the question I wondered is, can we apply this to forensics without knowing that much about who did what in the intervening months between the data theft and the investigation? Can we build a model of how file systems are used and look for patterns which survive all that intermittent usage? So let's make two observations. The first observation that I want to make is that I said timestamps are overridden. That's true, but they're not overridden arbitrarily. There's a very important invariant which is maintained. And that's barring tampering or malfunction. When a timestamp is overridden, its value will always increase. It will never decrease. For instance, if I open a file today, July 26, you come back from a month from now, you don't know what date you'll see, but you'll see a date greater than or equal to July 26. Barring malfunction or tampering, you'll never see anything less than January 26. And the second observation, which we need to apply statistical reasoning, is that file usage isn't uniform. File usage varies a lot. We find that when you look on a system, that there are a few very popular files which are opened constantly every day, every hour, many times an hour. But there are thousands and thousands of files on a file system which are very rarely opened, which hang around collecting dust. To elaborate on this second observation, I have here a quote from researchers Farmer and Venema. They were researchers at IBM at the time. I'll read you what they write. The vast majority of files on two fairly typical web servers have not been used at all in the last year. Right? That's something which you can look at your own system. You'll see thousands of files. Most of them you've never opened recently. And this is a common pattern, by the way, that researchers are finding everywhere, not just in computer security, and not just in computers, but in all areas of life, even in nature we're finding them. There are many names for this. There's, some people call it a heavy tail distribution, power laws, Pareto distribution. A great example, a simple example, is in language. In every natural language known to man, we have something called Zipf's law, which says the same thing for word usage. Right? If you think about the words we use, there are 100 or 200 words we use constantly. And those 200 words, they make up about half the words in a typical sentence. If, and, the, because, way. And then if you take a dictionary, there are thousands and thousands and thousands of words that you hardly ever hear. So this principle is the same thing in file systems. There are a few files which are always opened, and a moderate amount of files which are occasionally opened, and lots of files like Farmer and Venema report which are hardly ever opened. So what can we do with these observations? Well, like we said, when I copy the folder, all of its contents will have an access timestamp equal to the time of copying. If I come back and I investigate several weeks later, the first observation that I made tells me that all the files will have an access timestamp greater than or equal to the time of copying. None will be less than the time of copying. And the second observation tells me that there will be many files who, even weeks later, assuming the folder that was copied was large enough that we can use statistical reasoning, that we can apply the law of averages, but dealing with a large folder, we'll have many files whose access timestamp is still equal to the time of copying. These are all those unpopular files which are hardly ever opened, which collect dust, which got copied in the course of the data exfiltration, but haven't been opened since then. Okay. So as I was thinking about these ideas, I wanted to explore it a little further. And to do that, I built a simulator. And the simulator was a simulator of a file system, and it would randomly, throughout the course of every simulated day, it would open up files randomly based on the patterns that other researchers had already reported as to how files are opened. And at the end of 300 days, I plotted a histogram showing how many files were opened yesterday, how many were opened a week ago, how many were opened on a date a month ago, all the way back. And if you look, I got this heavy-tailed pattern, exactly what the researchers had predicted, where we see there's a decent amount of files that had been opened very recently, but a moderate amount of files that hadn't been opened for several weeks, and a large, long, heavy tail of files that hadn't been opened for many months, and even some files which hadn't been opened at all. And that was the exact same type of pattern which was predicted. And if you take typical file systems and you plot histograms, you'll generally see a pattern like this. Okay, great. I then ran the simulator again, but this time I made a change. I modified the simulator that on day 200, instead of just opening folders and files, it would copy the entire folder. Copy the entire thing, data exfiltration. Then I ran it for an additional 100 days, and I plotted the histogram again, this time in red. And you'll see something very interesting. It's true that in recent activity, we see very similar to the green case. And if I would just eyeball the data, I probably wouldn't notice anything. But we see two very interesting and very, very distinct differences, which jump right out of the page visually. Number one is that that heavy tail of the residual activity has completely disappeared. And the reason is because on the date of copying, all those files were open. And again, access timestamps, they go up, but they never go down. And all those unpopular files, which were just collecting dust and haven't been open for 6 months, but on the date of copying, all of those were open. And we still see, even when we're coming in 100 days later, we still see the results of that. And then even more importantly, we see this big cluster, we see this big spike here. We see, all those files that were open on that date. So we see two things going on. I call it a cutoff cluster. It's a cutoff because no file will have an access timestamp less than the time of copying. Right? We can come in a week, a month later, we'll still see that. And it's a cluster because many of those unpopular files have timestamps equal to the time of copying. So this is what the plot is. Again, when under normal activity, lots of files haven't been opened very recently. But in the case of data exfiltration, all files were opened on that date. And the only way a file's timestamp will change is if it's opened afterwards. But it will never be before that date. And a lot of files are opened afterwards. That represents this part of the histogram. But a lot of files are never opened in the subsequent month. And therefore, they just remain in this cutoff cluster. Okay, now what about the second problem I raised? That, okay, so we've used this cutoff cluster in histograms to distinguish routine access from copying, but maybe there are other things which also cause cutoff clusters. You could say that I'm guilty of the Aristotelian fallacy called affirming the consequent. It's true that a copying will create a cutoff cluster, but the converse isn't necessarily true. Cutoff cluster doesn't logically prove copying, right? There may have been other things, and we'll talk a little bit more about this later. But there may have been other things which cause cutoff clusters, and I have no logical proof that someone copied and stole data. Maybe they ran grep. That's entirely correct. I have no logical proof, and I'm not looking in a real case for logical proof. I'm looking to investigate. I'm looking for clues. I'm looking to do detective work. And we'll talk a little bit more about the type of detective work you do, but it's very important to realize that we don't necessarily need mathematical proof, and very often when we restrict ourselves to mathematical proof, we miss out on great data. We can investigate what was going on then, what systems were in use, who was there. We'll talk more about how to investigate in a minute. But I want to just make this point for investigators, especially for people such as myself who have a background in mathematics. Very often we put on this mathematical tunnel vision and we say, unless we have some type of mathematical conclusive proof, we don't want to look at something. And that's terrible. That really deprives us of lots of sources of great information, which are very useful. I have, again, another quote from Farmer and Venema. For some reason, this quote it's not well known, but I think it's very important for people in the field. Paradoxically, however, the uncertainty can actually give a greater breadth of knowledge and more confidence in any conclusions. So by allowing ourselves to look at things that we don't have logical proof and investigate based on those, we can learn a lot more. We'll talk a little bit later how to investigate. Before I go on and talk about an actual investigation, though, if any questions so far, if there are, there's a microphone in the middle. Someone could just go up there and I'll take questions now, or otherwise I'll proceed. Yes?
How about AV scanning?
AV scanning. Okay, great. That's a very important question. Things like antivirus scanning might go through the system and make similar patterns, backup software. So basically, when you apply this in a real case, you always know which system you're looking at. And what you have to do is look at those services that are on there and see what they're doing. In general, I've found that a lot of enterprise software, let's say backup software, will not modify access timestamps. It works at a file layer beneath the OS, and it's not going in through there. There was some great research done by someone at the Defense Department about AV scanning. He found out that most AV scanning will not modify access timestamps. Sometimes it will. What he found out is that when it's looking at higher level files like Office documents where it can't just look at the block layer, then you'll find access timestamps being changed. But in general, you won't. But there's no reason to be theoretical about that. Look at the system and see what's going on and look at control folders. We'll talk a little bit more how to apply this to a real case. But whenever you're looking at a real case, you want to see the other systems on there and how they're affecting the timestamps. Yes?
How do you account in your model for tampering, like time stopping and so forth?
Great, okay. So the question was, what if someone's tampering with access timestamps? So in general, well, first of all, when we're dealing with an insider, most of the time we have to approach it from a different perspective than an external penetration. When you have an external penetration, the person is by definition someone with a large amount of technical sophistication, and they know how to reach into the file system and kernel and mess around with things like timestamps, and they can do things. Most of the time, a typical insider, that's not even a suspicion, they don't know how to do things. If you're dealing, and that was, for instance, the case which I was dealing with, the person was not an IT professional. Now, if you're dealing in a case in which you have a professional or a sophisticated technically adversary, well, then, if they just monkey around with the timestamps, it's very rare they'll create that histogram. They might create another pattern which looks very unusual. It might not be the cutoff cluster, but it'll be something which is just unusual. It might not give you the same information, but it'll let you know that something very odd is happening. But again, most of the time, you're not going to be looking in that direction.
Yeah. What methodology did you actually use to develop your simulator? Like file system, operating system used, applications in use, actual enterprise operations that are being run? Or did you just develop the simulator to confirm the logic that you've already laid out for us?
Right, okay. So the question was, how did I implement the simulator? So the simulator was a test of the model. It was done over 300 simulated days, but it ran very quickly. I actually built two different versions of them. The first one was done in Python, and it uses certain mathematical equations. The second one was done using more sophisticated modeling software called AnyLogic, which is it's a modeling package which let me do lots of different types of experiments. But the simulator actually never reached into the file system. We'll talk a little bit more later what you said about what happens when you actually try this, reaching into file systems and actually copying files. What behavior do you do? At this point, it was done as a simulation. It wasn't actually using live file systems at this point. Yes? Great, okay. So I was primarily working on Windows systems. I was looking at Windows Server 2003, Windows XP. We're going to talk a little bit more about different behavior, different operating systems as we go on.
Did you consider Vista and Windows software that it's evil, how access updates by default?
Great, okay, so the question was that there are certain versions of Windows which by default don't have access timestamps, and that's correct. So if you're on a system like that, like Vista, which by default has access timestamps, then you can't use this directly. Could you use different versions of this? Perhaps we'll get to that later. That's more of a research question. But again, in a real case, the first thing you're going to do is look at the system and see, did they disable access timestamps? If they disabled it, then you can't use this method as is. Okay, so I'll tell you a little bit about investigation now. I can't go into too much detail, but I plotted, this was the case my client was interested in, I plotted these histograms for a whole bunch of folders. And most of them were what's called control folders, folders that were of any particular suspicion. And for most of those folders, I got the exact heavy tail distribution which we predicted. For two of them, I actually saw cutoff clusters. Now, the first one, I had no reason to believe that I would see a cutoff cluster. It was a control folder. And it wasn't too hard to investigate. There was an authorized copying. I found out who did it, what he had done, plain and simple. The second one really shocked me, because that was the exact folder which had the data which was suspected of being copied, of being stolen. And here, this addresses some of using these control folders gave me a lot of evidence that I didn't know if it was stolen. Maybe something else had happened, but something very unusual had happened that hadn't happened on any of the other folders there. And I had, the beauty of this method is not only did I have reason to believe that something very unusual had happened, but I had a very specific date and a rough window of time to investigate. Now with this in hand, I was able to use a lot of other means to investigate. I was able to look and see who was in the building and what were they doing. I was able to speak to people and use both legwork and interviews and other technical investigations and propel the investigation forward. So that's how I use this in an actual investigation. Okay, now I'd like to address some of the the real world concerns that you had raised about what actually happens when you do this on a file system. Okay, so when I first, this is way back in the lab, I jumped to the real investigation, but let's get back to the lab when I was working and trying to crack this case for my client. You know, this case was valuable enough that it wasn't a typical investigation. It was more of a research project. But I like solving problems that haven't been solved before. So when I first started looking at access timestamps, I just saw lots of noise. Lots of noise. I didn't see at all when I copied files anything that had made sense to me. I was pretty confused. And I took a step back and tried to think, is copying a file, is that even considered an access? You know, I made an assumption here that copying something should be considered an access, but perhaps my assumption is completely incorrect. So even though I was working with Windows, I decided to start with Solaris and Unix systems because they're open source, a lot easier to figure out what's going on. And I have here part of the source code for the copy command in Solaris. And if you look, you see something interesting. How is the copy command working? What is it doing? This is only a snippet. You might not be able to see the whole thing. Does anyone notice anything? How's the command working? It's opening up the source file, reading it into a buffer, and then writing the file, the buffer back out into the destination file. It's basically not doing anything special. The entire copy is being done in user space as if it was any other source of data that you wanted to read or that you wanted to write. The fact that we're copying is of no value or no interest to the copy command. Now, it's interesting. There is no copy system primitive in POSIX. There's read and write and open and close. There's no copy primitive. Interestingly enough, in Windows there is. There's a copy file primitive provided by kernel DLL, which copies a file in one command. Now, this makes sense. Solaris, Unix, Linux are open systems. They work on the power tools philosophy, which basically says mix and match different components, use them in different ways. And there's no reason the kernel, the OS level, should be concerned at all copying a file. If you want to copy a file, do it yourself in user space. Read the file, put it into memory, write it out. And it makes sense that that would be considered an open because there's an open going on, right? I highlighted the open command there. And in fact, on Unix systems that I experimented with, I saw that copying a file did change the timestamp. However, in Windows, copy file is done with privileges in OS space. It's done using a system call. And that makes sense with the Windows philosophy. Windows is a closed system. The file system is tightly integrated into the operating system. And by integrating the copy command and giving us a copy primitive instead of using reads and writes, Microsoft can do certain optimizations which you couldn't do otherwise. So it makes sense that from the Windows perspective, and further experimentation and a little reverse engineering confirmed this, there's no open going on, there's no close going on, there's no read going on. And copying a file doesn't touch the access timestamp. This might be pretty disappointing. I don't know if I was disappointed at the time. I was still in the research phase and you used to hitting bumps at that point. But then I realized, okay, there's a copy file primitive in Windows. Is there a copy folder primitive? Does kernel allow you to copy a folder in one sweep the same way it allows you to copy a file? And there is no such thing. So how does Windows go about copying an entire folder? Well, interestingly enough, that is done in user space. You have to open up the folder, like a regular, anytime you want to open up a folder. You have to look inside its contents, like anytime you're looking inside the contents, and then copy those files individually. Wow, that's pretty neat, because a folder, a directory, is really a file also. And when my client code, my user code, wants to open up that folder and see what's inside, that's a regular read on the directory, on the folder. Not the files inside it, but the folder, the parent folder. And parent folders have access timestamps. So even though we don't have any access timestamps on the files inside, but we have access timestamps on the folders and on the directories. And when I did that, when I filtered out all the files and only looked at folders and subfolders, all the noise went away and my data fit in very nicely. And this is very gratifying. Not only had I overcome the problem, but I actually turned it into a virtue. Because now this means that in the case of copying, we're going to see something very distinctive on a Windows system. We'll see files will have one access pattern, and folders will have a completely different access pattern. And so by plotting those two separately and comparing them, it gives us even more confidence that large-scale copying took place. Okay. Now, what about accuracy, right? Anyone who's done forensics work with access timestamps, no, very often they're inaccurate. They may be off by minutes, they may be off by hours. So here, the beauty of using a stochastic-based model as opposed to an artifact-based model really shines. Because we don't really care about accuracy. We can throw in lots of noise and lots of randomness. We can even be missing part of the data. As long as we have enough to infer statistically and make those plots, the method works beautifully. Okay. So now how do you go about doing this in a real case? I don't yet have a push-button tool. I'll tell you in a few minutes about what I'm working on, but that's a while off. Right now, it's something which has to be done by hand. And my goal here is that after this session, you'll know enough to go back and apply this method yourself. If you just take a bunch of access timestamps and you plot the data, you'll see nothing. You're just going to see noise. There's no way to eyeball this. I've tried, and you don't even get a clue. So there are different ways to go about looking for these cutoff clusters. But the method I'm going to present now is called filter and plot. And what I like about this method is that it's very visual. It works not by using math and statistics directly, but by using our visual cognition. And there's a few steps to the method. The first step is to filter. If you just plot a histogram of the entire file system, you'll see noise, because unless the entire file system was copied, which very rarely happens, all the folders and all the data, the OS data, the executables, all that stuff, temporary files, which weren't copied, will drown out any cutoff cluster from appearing in your histogram. So the first thing you want to do is separate out your folders into different buckets. You want to put the folders you think may have been copied into some buckets, and you want to have, let's say, about a dozen control folders that you think weren't copied. Put those all into different buckets. The second thing you want to do is split each bucket in half. This is very important on Windows. You want to have directories plotted by themselves and files plotted by themselves. So split those two buckets in half. Next, you want to take out from these buckets any files you think that the exfiltrator may not have been able to copy. Files which are system files, hidden files which they don't have read permission, files which would be skipped over, folders which would be skipped over in the copy operation, remove those. We don't want to skew our data. And then finally, there might be other things to remove also, and here where it takes a little bit of creativity and a little bit of experimentation. But depending on the suspected means of copying, certain things may not have been copied. A simple example, on Unix systems, a file whose first character has a period as a dot is considered a hidden file, and that won't be copied. So you want to filter all those things out manually. Once you have these buckets, and these buckets have been split and filtered, let's just go over that. So it's 4 steps. Put the stuff into different buckets, and most importantly are the buckets you think may have been copied, but you also want control buckets. Split those buckets into 2, and remove things that would not or may not have been copied. Then build those histograms. And what I really like about those histograms is, as someone asked before, they'll capture lots of different patterns. If someone's monkeying around the data with using timestamp, you'll see a different pattern here, but you'll know something's up. The tool I use to plot is Ploticus, but there are many different tools you could use to plot those histograms. Okay, so now you have these plots, and you've looked at your folders, and you either see cutoff clusters or not. Don't make the mistake of assuming anything at this point. A cutoff cluster is not proof of copying. We have to advance the investigation forward. And these are steps that I call interpret and advance. If we don't see a cluster, that's strong evidence that there was no copying. We see this typical histogram, heavy-tailed histogram with no clusters, so we have very strong reason to believe no copying took place. If we do see a cluster, we're not done. We have to do 3 things. The first thing is to look at the control folders. If we're seeing lots of clusters, lots of different places, then we might be something unusual on the system at a system level, which is causing cutoff clusters to appear lots of places. Whereas if the control folders are pretty much absent and free of cutoff clusters, that makes the cutoff cluster on the suspected folder very, very significant and very important. The next thing we want to do is look for causes. Someone mentioned antivirus software. We want to catalog the system, look at everything that's running on it, antivirus, backup. If it's a very technical and sophisticated user base, we're going to look for command line grep and command line recursive directory listings, different types of command line options which may be causing similar things. Most offices, no one's even heard of that stuff. They're not using it. But if they are, it's pretty easy to find out. If they are, you can look in histories, you can look at the files, these tools are even installed. We want to look for other possible causes. And the third thing we want to do is to fingerprint the cluster. I'm not going to go into too much detail here, but if you notice, we identified 4 patterns in the beginning, and the cutoff cluster doesn't really use all the nitty-gritty of those patterns. It's more of a yes or no thing. But by looking at the exact sequence, what type of recursion is in place, the speed, the selectivity, we can distinguish copying from grep, and we can even distinguish different tools used to copy from each other. So I'm not going to go into that right now, but that's a third thing which is worth doing. Now, once we've done that, we're not done. The cutoff cluster is more than anything else a means to propel the investigation forward. It defines a very tight window of opportunity. It will let us know, well, we really don't think someone copied this data in the past 3 weeks. But 3 weeks and 2 days ago, something very unusual happened sometime between 10 p.m. and 11 p.m. Investigate further, see what you could find about that. Okay, so before I go on, I'll take any more questions. Okay, so I think this method is very useful. It's been very useful to me. But what about implications for the field as a whole? So here I'd like to talk about something which I call forensic hacking. I define hacking. I said I've been an independent consultant for about 10 years. I've been a hacker for about twice as long. And I like to define hacking as exploring how something works by using it in a way that its creators never imagined. And buffer overflow is a great example of that. And the first time I did a buffer overflow, I found it fascinating. After I'd done it about a dozen times, it wasn't much of a hack anymore. It was pretty monotonous. This is a real hack, in my opinion. This is a great way to use an operating system in a way it was never intended to explore how it works and to answer some very valuable questions. And the reason I'm saying this is I think there's a huge need in security in the defense space, not just in the attack space. A lot of people work with a hacker, with hacking capabilities, with a hacker mindset, who like to explore, are working on new means of attack. That's very important, but we need to work on defense also. In the keynote yesterday, Sean Henry from the FBI pointed out that to him, the question has changed. The question that he's trying to answer isn't anymore, is there someone in a perimeter? Isn't how to keep someone out of a perimeter. The question, he says, we know there are people in our perimeter. How long have they been there? What have they been doing? What data have they taken? And we don't really have the means to answer those questions yet. And I think this is a very big opportunity for people in security who have technical mindsets to get into, to start looking at some of these messy questions, these sloppy questions, and use operating systems in ways they were never intended to answer these questions. To be more specific, how does most forensics, which is used in the field today, work? Most forensics, which is available today, comes from data recovery. And the way it works is we start off looking at the data which survives. From the surviving data, we reconstruct the previous data. And we deliver that previous data as a deliverable, right? We might undelete files. We may reassemble files from fragments on the operating system. And we say, these are the files we found in our investigation. That's nice, but that's not really what we need. Leading researchers, leading people in law enforcement are all telling us what they really need from us is the ability to know what people did, what happened. And here classical forensics is really stuck. And I think using things like stochastic forensics really help. The beauty here of stochastic forensics is that it turns the whole process on its head. Instead of working from data and working back to reconstruct, we go in the opposite direction. We ask ourselves, what do we want to know about? In my case, it was data exfiltration. In your case, it might be other things. We say, okay, what behavior is associated with data exfiltration? What does the system look like? We build models of how systems work, and then we say, well, okay, if this behavior went on, we'll expect a system to look one way. And if a different behavior went on, we'll expect the system to look in a different way. We can model those, and we can measure those. We might not have Aristotelian proof, but we can still learn a lot and answer some very interesting questions. And like I said, forensics is a great tool to answer these questions. And I think it's something we should embrace. One thing which I'm working on now, which is outside the scope of this talk, but just to give you a flavor, is database forensics. There's a lot of people who really need to know. We know we had a penetration. We know we had an intrusion. What data did they steal from our database? Are very often cases of forensic accounting, fraud, embezzlement. We want to know, was someone tampering with our financial data? When were these records changed? And very often we can't answer those questions, but we can use similar approaches. Look at the B tree, the index the database uses to index the data, and there's no way to predict based on the data what the B tree should look like, but we can use a similar stochastic process, model what the B tree will look like if someone tampered it, model what it will look like if someone didn't tamper it, and draw inferences also. So I think there are a lot of implications to change how we do investigations. Not just be data focused and artifact focused, but actually start answering some of these sloppy questions. And these are some of the things that I'm working on now further. Number one, I said that right now this method is not a push button method. Turning into a push button method is not very hard. But if I were to give that out now, it would be a big mistake, because right now I'm happy that to use this method, you really need to understand it. You need to know a little bit about operating systems and forensics. Before we can make it a push button method, we need to investigate it further. So of course we have to automate it. But what's really important is to do a large-scale scientific testing across a broad corpus of data. There's lots of corpuses which forensic investigators and researchers use to test their methods, but most of them are narrow slices. What I really need are slices of data, not slices, captures of data for offices over months and weeks, typical offices, people accessing data in different ways. I like to test this method across these types of things and validate it. Now, building a corpus like this, what does an office look like after a year of data, be very valuable for me, be very valuable for other forensic researchers also. I'd like to build confidence levels. How reliable is this? Can we actually use the model to give us a probability value? We could say there's an 80% probability that data was copied on this date. I'd like to validate in lots of different cases in the presence of different operating system versions like you pointed out, or different antivirus versions like you pointed out. And the second thing that I'm working on is fingerprinting. Like I said, there are ways to distinguish grep from copying. There's different, if you look at for instance, one way is the order of recursion. There are different recursion orders. What order are we opening up files? The speed is a very other interesting way to make those fingerprints. That's another area to look at. And then, perhaps most interestingly, I'm interested in what other questions can stochastic forensics and can other non-artifact-based forensic methods answer. Let's look for these sloppy questions. Let's answer them with less precision. Okay, so I'll take any additional questions now. Yes?
Could you zoom out, change, and look at like a central repository of data? So lots of people accessing a set of files. So different groups might have some set of files we work on usually.
Could I ask you to go to the microphone? I'm just having trouble.
Hey, this on?
Okay, so just I'll listen carefully.
Sorry.
Okay, so just say it again. I'll listen carefully.
Have you looked at like a data repository? So you have a lot of users accessing the files for each group of users. It only restricts the access to the set of files.
Okay.
So does that change the model?
Okay, so the question was, what if you have a large group of users, but within those groups there are certain subgroups and they're not all accessing the entire repository? So the neat thing about this heavy tail distribution is that when you zero in on it, on one part of it, you see the exact same pattern. For instance, if you would graph the distribution of word frequency in the English language, you'd see this pattern. If you would cut out one small slice of it and then zoom in on that, you see the exact same pattern also. That's a neat property of this, let's say the Pareto distribution, is that it's self-similar. As you zero in on any small subslice, you'll see the same thing. Same thing with wealth. If you take the 1,000 wealthiest people in America and you graph their wealth, you'll see that pattern. If you take just 10% of them, you'll see this exact same pattern also. So I think if you have, even if you have a subgroup which is using it in a certain way, you'll still see that heavy tail distribution within that subgroup. Okay, any other questions? Okay, thank you very much.